Question 2. A sample of sulfur consisting of 3 isotopes has a relative atomic mass of 32.16. Table 1 gives the relative abundance of 2 of these isotopes. So that means 91.0% has a mass of 32, has atoms of a mass of 32. 1.8% has atoms of a mass of 33. Use this information to determine the relative abundance and hence the mass number of the third isotope. So there's a third one that's missing. Give your answer to the appropriate number of significant figures. So now we've got to work out what mass the third one has and also what abundance it has. Well, there's only 3 isotopes, so if one of them, if the atom's 32, the isotope with a mass number of 32 is 91% and this one's 1.8%, then 100% take away 91, take away 1.8% will tell you that 7.2% is the remaining isotope. So 7.2% is this remaining isotope, and we don't know what mass it is. We know that the average is 32.16. So what we've got to do is imagine there's 100 particles. 91 particles have got mass 32, 1.8 particles have got mass 33, and the remaining, which is 7.2 particles, have the mass whatever that is. So the mass of these particles of mass 32, there are 91 of them out of 100, so 91 particles, each mass 32. We'll work out the mass of those together. There are 1.8 particles mass of 33, so 33 multiplied by 1.8 is the mass of these particles, and there are 7.2 particles of mass that we don't know. Let's call it y. If we divide by the total number of particles, and there's 100 particles, this will give us the average, which equals 32.16. Multiply both sides by 100, or so you can multiply both sides by 100 and then work out these values. 32 multiplied by 91, 33 multiplied by 1.8 will plus y times 7.2, 7.2y will equal 3216. Take these values across to the other side, and 7.2y will equal 32.16 multiplied by the 100. Take away 32 times 91, take away 33 times 1.8, because these are coming across to the other side, so they're going from positive to negative, and that equals 244.6. Divide both sides by 7.2, so y is 244.6 divided by 7.2, 33.96. It's got to be two significant figures. It's got to be a whole number essentially, because isotopes can't have odd numbers, so we'll round it up to 34. So its mass number is 34. Describe how ions are formed in a time-of-flight mass spectrometer. Well, they're bombarded with something called an electron gun, and the electron gun removes electrons from the atom. So the electron gun, which fires electrons at the particles, then hits the particles and removes an electron from the particle. The electron gun fires out high energy electrons, so fast moving electrons. So you hit the sample, the atoms in the sample, by high energy electrons fired from an electron gun, and then the sample loses an electron, forming an ion or a particle with a plus charge. We've called the particle M here. But it's essentially a particle that's lost an electron and having a plus charge. The time-of-flight mass spectrometer can be used to determine the relative molecular mass of molecular substances. Explain what is necessary to ionize, in other words, turn the particles into plus ions when measuring their mass in a time-of-flight mass spectrometer. Well, you need to accelerate them, so what you have is you have plates with small holes in them that are negatively charged, and the plus charged particle that you've just made is accelerated these plates. It goes through the plate and then hits a detector. When the plus charged particle hits a detector, it turns back into an atom, so the plus charged particle gets its electron back off the detector plate and forms atoms, and that generates an electric current that we can read. So ions, so plus charged particles, not molecules, will interact with and be accelerated by the electric field. So these plates, charge minuses, accelerate the ions towards them down the tube. and the ions create a current when hitting the detector. So the way that works is the plus charged ion gets an electron back from the detector plate, and to form atoms rather than ions. So it gets its electron back and loses its plus charge, and in doing so it creates a current, and then we can read that from the detector.